You know, humanity is a disease, and cyclonite is the cure. Just kidding. Just joking. What a terrible joke. Fifth installment of the energetic series, we're covering RDX. RDX, huge topic, massive topic. There's no way I'm going to be able to cover it adequately. I'm just going to have to pick and choose. So I guess these are things that I would want to know if I was learning fresh about the topic of RDX. That's what I'm going to tell you. Basically, you're just like my boy. Okay, I'm going to teach you just like my boy. Here we go. Okay, so let's talk about the name first. So you have RDX. That's what everybody knows it as today. Back when it was being produced in huge capacity in World War II timeframe, it would be known industrially as cyclonite. So those are the English vernacular terms. The RDX is actually a code name, research department explosive. It's a British code name. Really great code name. But that's what it's known as today. So that's English. If you went to the German bloc countries or like Sweden and, you know, Austria, Germany, stuff like that, they're going to know it as hexagen. So it's different terms depending on where you are. The Germans themselves are the discoverers and initial developers of RDX. And then quickly prior to World War II, you get all the other nations concurrently developing their own strategies to produce RDX. So, for example, in Germany, you have Dr. Jörg Henning. In 1899, he files initial patents. Now, he filed it he's a pharmacist, and so his patent is filed for medical purposes. It wasn't until a little bit later in 1921 that you started to get some published findings on additional research on the explosive potential and character of RDX. And so you see, like, I know Edmund von Hertz is working on it. He's the guy that developed lead styphnate. He did a lot of work for Germany. You have Friedrich Lenz that works on it in the 1921 timeframe. This is all concurrently. In the United States, you get Hale. He's out of, I believe, Picatinny Arsenal in New Jersey, developing for the initial development for the United States. And Hale actually published a lot of the first literature findings on the explosive character of RDX. I really can't stress to you enough how much RDX changed the face of warfare. It was an entire new tier of a bracket of energy available in explosives that wasn't available before in both jet velocity and pressure. There was Petten prior to this. Petten is practically equivalent, in terms of explosive force, but it wasn't producible on a huge scale because of the precursor for Petten being acetaldehyde, which is more difficult in mass quantity versus, you know, ammonia is very abundant and easily sourced by nation states. And so when you have an easy, simple precursor, you know, like toluene for TNT, it's mass produced along with its mechanical benefits. And then when you have something like RDX that is derived from ammonia, it gets mass produced too, especially because it has extreme explosive potential. So at the height of World War II, you have Germany producing 7,000 tons of RDX per month, and the United States was producing 15,000 tons of RDX per month. Just to give you an idea of the scale of mass production going on at the height of the war. So with the introduction of RDX, you get huge advancements in both explosive technology, but also the theory of explosives is also further developed. The relationship between density and high performance is pretty clearly revealed with RDX. You have new munitions technologies like shape charges, cutting charges, penetrating charges, things like that. All that stuff comes with the advent of RDX. And then you have the technological problems of how do you carry this explosive, because unlike picric acid or TNT, which are melted at a high density, to fill into odd shapes, things like that, RDX is a powder. So you have to pack it into some simple shape like a cylinder. But if you don't have that shape, it becomes a lot more difficult of a problem. So to overcome this, the United States came up with some classification systems, the compositions. Composition A's are all going to be wax-based. So they're using wax as a simple desensitizer that also allows them to pack it in. Then you have composition B's, that would be milk cask carry of TNT. And then you have composition C's, those are going to be non-energetic plasticizers that act as a carrier and a desensitizer for C4, making it able to be shot with a rifle, things like that, not detonate. Other than munitions and device use for RDX, you also have detonators. It is less efficient than PETN. PETN is more efficient at small masses. RDX becomes more efficient when you get into larger masses or payloads. PETN is a little bit more sympathetic to external stimuli to cause the detonation, so it's more suitable with a lower critical diameter, slightly, than RDX. In terms of what it actually is molecularly, it's a trinitrohexahydrotriazine. So it's a triazine, bone structure with 3 nitramines on it. And the nitramine would be a nitro group attached to an amine group. So this has 3 of them symmetrically. It makes a cyclic molecule. It's very resilient and metastable chemically. It's a very stable explosive. That's what RDX is really famous for. To give you an idea of the stability, RDX withstands 120 C temperatures at 62 hours and has no acidic decomposition products. So it's a very stable explosive, much more stable than PETN. Obviously, the power on RDX is pretty extreme, and that comes with, typically, you'd get more sensitivity with that, and that's true with RDX too. So RDX is about 3 times more sensitive than TNT. And like other explosives, a lot of them, at increased temperatures, RDX becomes more sensitive. So it's twice as sensitive to impact stimulation when it's heated to 100 C, which is room temperature. Okay, let's get into some stats for RDX. So the theoretical density, max density, is going to be 1.806 grams per cubic centimeter. That'll come with the theoretical detonation velocity of 8.8 kms. To give you an idea of the range because that's a theoretical max density. The true performance is going to be based off of whatever you pack it at, that density. So when you get down to 0.8 grams per cubic centimeter, you'll be at 5 kms. When you get to 1 cubic centimeter, just over that, you'll be at 6 kms. And then at 1.7, you get 8.3 kms in detonation velocity. There is a detonation velocity equation. I'll put that on the bottom of the screen here so that you can see that. That'll let you, the P on there is your density. So you just plug in whatever density and then that'll give you your detonation velocity. And it's pretty accurate. Then of course you have pressure. 33 GPa is what is commonly cited for RDX. I have some literature that cites 1.767 grams per cubic centimeter. At that density you get 33.8 GPa. So it's very high performance in terms of pressure and det velocity. All the references that I'm using for this video are practically 99% of it is found in Chemistry and Technology of Explosives, Volume 3 from Urbanski. That's available online. The other one would be a TM, a technical manual, TM 9-1300-214. Both excellent references to get better general understanding of RDX. As for the less exciting, characteristics of RDX, you have melting point 202 to 207 C, ignition at 229, that's when it goes up in flame. It's pretty aggressive and it's burning. There's a lot of energy stored in RDX as a metastable material. And you can really, a lot of times when you're nitrating this and creating it, you can really get the sense that you're loading some kind of pistol here. I mean, there's just a lot of stored energy packed into RDX. The critical diameter in RDX is commonly considered to be about 1 millimeter. Oxygen balance is for CO2 minus 21.6%. Okay, one of the interesting things about RDX is its pyrovalence calculation, which is lesser known. Oxygen balance calculations are similar to pyrovalence, but it's based off of the in-state valences after explosive redox takes place. You're calculating if the molecule is a net fuel or net oxidizer. In a complete picture. So for RDX, it comes out to +6 if you solve the equation for CO2. +6 is a net fuel. That means that it acts as a fuel. And that's pretty typical of common secondary explosives. But RDX and HMX, both of them, are unique in that if you calculate based off carbon monoxide as opposed to carbon dioxide, you will get a net balance of 0, which means it's perfectly balanced. In that case, it would be as efficient as it can be in terms of the energy potential release during the redox. There were some studies done on RDX decomposition products after an explosion. So Avogadro found that 25% carbon monoxide is produced and 20% CO2 is produced. So it's actually favored in the standard blast profile of RDX. Carbon monoxide is a little bit more favored. If you could push it more towards carbon monoxide, you probably get additional energy. It's just kind of an interesting fact about RDX. A couple last things before we get into production of RDX. So you can desensitize RDX with a 15% or greater water content. In that case, it wouldn't detonate even with a number 6 cap. So water is a effective desensitizer for RDX. All right, solubility of RDX, you want to know that because you have to recrystallize it. All secondary explosives you want to recrystallize usually 3 times. Anyways, it is effectively dissolved in acetone at 56C, which is close to boiling point. You get 57.27 grams of RDX dissolved. And these will be for 100 grams of solvent. That's kind of a standard table. So the other 2 that are really effective but lesser used because they're much more expensive would be cyclohexanone and dimethylformamide. So cyclohexanone gets 27 grams dissolved in at 97C, and the dimethylformamide is all the way up to 42 at 100C. So dimethylformamide is by far the most effective, but acetone is common, and that's what 99% of people are going to use. Okay, now we get into production and general manufacture of RDX. This is where it gets really complex. There's a lot of confusion about RDX, and the reason why is because nobody really knows anything about RDX. There have been multiple generations of chemists that have devoted their entire careers to the study and development of RDX. So there's a lot of work done on it, but what is going on with the reformation of the molecule from hexamine into RDX is really not well understood. It's kind of a mystery. So there are a lot of theories of it. Some of them work pretty well, some of them work better than others. But overall, you should understand that people really don't understand what is going on with RDX, and that's okay. The point here is that you really want to look at the synthesis of RDX as an understanding of the broad behavior of what happens and why things that happen. That will help you come up with a good synthesis route for yourself to effectively produce RDX. With that, the first confusion to knock out would be HDN. So HDN is hexamine dinitrate. Hexamine, I suppose we should mention that. So hexamine is the raw precursor that you'll use with nitric acid in pretty much any instance of most instances of producing RDX. Hexamine is formed by the condensation of formaldehyde and ammonia. Hexamine dinitrate is formed as the double nitrate of hexamine when you hit it with a low concentration nitric acid like a 68% nitric acid. Okay, so hexamine dinitrate, it's a hygroscopic white crystalline material. It is an explosive in and of itself, but it's not high performance. It's barely usable. HDN is one of the preferred routes to RDX, especially in amateur circles, and it just kind of has the impression of being an easier way to the synthesis. The reason for this is because the heat of reaction of HDN is about twice as low as hexamine. So if you use straight hexamine, it's extremely exothermic. It has twice the heat of reaction as HDN. And so the end result of this is that when you nitrate hexamine in either form, you'll notice a distinct difference in the speed at which you can nitrate it and how angry the reaction gets, how much hissing it puts off, how much thermal energy is produced, how high your temps go. So that makes people go with HDN more, but HDN has the penalty of time. So for overall efficiency, you are actually getting a faster product if you just slow down your addition and use hexamine than if you go through the process of producing HDN and then drying it out so that you can correctly weigh it and then use that for your RDX. There is no advantage in terms of yield gain from using HDN versus using hexamine. It's just a smoother reaction generally. Most of the routes to RDX, common routes, will yield somewhere in the 70% range, 70s, high 70s. That's pretty common for most routes to RDX. Nevertheless, any comprehensive guide to RDX should cover HDN to clear up confusion and make it more understood, what is going on. So let's cover HDN. I would reference the Hale and Bachman procedure. It's floating around on the web. There are other methods. There's a method where nitric acid is dumped in all at once and you get a really dramatic precipitation of HDN. It jumps out of solution, physically forms and rises out of a solution, and it's, like I said, it's somewhat dramatic. It's cool to see. That route, you're going to get a temperature spike and it exceeds the recommended temperatures. So you might get contaminant products, methylene products that in with your HDN. They can probably still assist in forming RDX, but it may actually lower your yield doing that. Regardless, the HDN produced with the dump method is a lot less stable thermally than HDN produced by the literature procedure. So we'll do Hale and Bachman. They take 20 grams of hexamine, they mix it with 35 milliliters of water, and they stir it until it's dissolved, and they're doing it at 2C. I've found that it's not necessary at this point to be strict with temperature. You can dissolve hexamine in water at the higher temperature, and it doesn't seem to cause any penalty. But Hale and Bachman do it at 2C. Then 65% of HNO3, it's added dropwise at a temperature below 10C. The maximum temperature you want to get to is 15C, but Hale and Bachman recommend 10C, so I would just stick with that. After the nitric acid is all in and all added, you continue stirring for 15 minutes and you continue cooling and try to keep it around 5C by the time that you're finished. This is going to yield 86 to 98% theoretical for HDN. And so the procedure here in terms of the quantity, you would just spec out your quantity depending on your needs. You would use 1 gram of hexamine to 1.38 grams of HNO3 at a concentration of 65%. So at this point you've made HDN, it's in solution, and you need to filter it. So you don't crash it or anything like that. You just take the acidic solution with the HDN, you're going to put it through a filter. You can wash it with acetone. So run it through a filter, then put acetone on top of it for 20 grams starting hexamine. You can use somewhere around 100 milliliters of acetone. You pour it over the HDN. It's going to pull out some of the water and assist in making the HDN dry. So now that the HDN has been filtered and it's ready to be evaporated of all traces of acetone, you want to do this because acetone reacts with nitric acid and produces a lot of heat. You don't want to be using it in your RDX synthesis. So you got to get all the acetone out. The best way to do that is to use an air current, blow air across the HDN to begin drying it out. And then what I prefer to do after that is use a silica or an absorbent, something that's going to pull water, moisture out. You can put HDN in the filter in a bag with a bunch of silica gel to pull water out. That's my preferred method. What you don't want to do is try to use heat to assist. Unlike other materials, HDN is really pretty sensitive to heat, especially if you're doing, if you have some contaminant products in it. You can actually cause decomposition and release nitric acid. So if that happens, you're going to notice at first a smell. You'll have an acidic smell in the HDN, and then as it continues, the HDN will turn into kind of a putty instead of a crystalline material, and then eventually it'll exude orange. I assume it's an acidic product. So you don't want to use heat, just avoid heat. You can do it at room temperature. You can use air, and then you can use a absorbent to pull moisture out. And then once it's all dry, you can measure your yield on HDN. And then now you're ready to spec out your procedure for RDX. So as you can imagine, this is kind of a complex endeavor to properly go through HDN synthesis. A lot of the amateur methods to produce HDN for the purpose of RDX really don't even take this into account. So they're kind of on the sloppy side, but regardless, they'll work and you'll get a yield. RDX is pretty forgiving, although it does have some thermal dangers and sensitivities that we'll discuss coming up. I know, it seems like it's kind of overwhelming, all the data in this video. That's just the nature of RDX. So I'm going to try to give you some generalities on the behavior of RDX when it's being produced, and kind of talk about some of the historical methods that were used during wartime to produce RDX, which is where, you know, all the synthesis methods come from. Okay, so the first two methods that I'll discuss are British method and S.H. Saul's method, which is a German method. These were both used in wartime, and they're both dealing with straight nitrolysis of regular hexamine. So they're hitting hexamine with a concentrated nitric acid to produce RDX. They're approximately equivalent. The German method is a little bit lean on the HNO3, so it actually saves some HNO3, and it uses a little bit more hexamine, whereas the British method uses less hexamine and more nitric acid. So we're not going to discuss those in too much detail. Some different methods would be the K method or Knopfler method. This one's really interesting, and this is this is my preferred method. So we'll go into that when we actually do it after we discuss the other ones. W method would be the Wolfram method. That's a really interesting method that isn't, it has a pretty decent yield, but it's not practical economically on any kind of scale. And it's kind of, more difficult precursors, so it's not going to be used. But just for information, the W method would be sulfamic acid, formaldehyde, and HNO3, producing RDX in 80 to 90% yield, which is pretty good. The E method would be paraformaldehyde, ammonium nitrate, and acetic anhydride to produce RDX. And then you have the Ka method, which is, this is also the same as Bachmann. So Bachmann is a term for a method in the United States that was used, and it was developed concurrently with the Ka method, which is a German method. And this involves HDN, ammonium nitrate, and acetic anhydride. And they're producing RDX. A lot of these are in the 70% yield range. You can actually get higher, but that's kind of the common range of your theoretical yield that you're going to get, which is somewhat low, especially considering that you're using acetic anhydride. So we're not even going to go down that route or discuss it anymore, just mentioning it so that you understand the routes to producing RDX. So just for covering the complete story here on our RDX, another route that's less common is the nitroso RDX route. So the nitroso RDX is it's missing some oxygen. It is the product of sodium nitrite treatment with an acid like muriatic acid on hexamine. It's a very gentle reaction, and your product is the nitroso RDX, which is explosive in itself. It's a little bit lower powered than proper RDX. You can then oxidize it to RDX using nitric acid and hydrogen peroxide or other things. There's theories that you could use oxone, which is usually available as I think it's like a pool chemical stabilizer in hardware stores. Anyway, that is I've done a lot of research on nitroso RDX. It is a really windy rabbit hole that is unexplored, and we're just not even going to go down that road at all. It's a huge waste of time for anybody that's trying to efficiently produce RDX, so I wouldn't recommend it. It does have the advantages of producing a chemically pure RDX that is free of HMX, because all of these methods that I've already discussed are going to incur a contaminant of HMX in 8 to 12%. That's just what they always do, except if you go the nitroso route. So you take a huge yield penalty, but you get chemically pure RDX.